right, well, good evening, everybody. Welcome to the final Astronomy and Astrophysics public lecture series of this academic year. That's so great. Our first one of the next academic year will be August 22nd. And unless I can find another speaker, I'm thinking I'm going to speak about, yes, we are all star stuff, sort of nucleosynthesis, a little about Carl Sagan, stuff like that.
Billions and billions.
Billions and billions, yes, indeed. You don't have to come, Mark. So let's see. Before I introduce our speaker, I would like to say a huge thank you to the Florida Tech Student Astronomical Society. They're the ones that have been manning the telescopes and showing all of you the skies after our talk. So if we could, round of applause for them, please. Thank you very, very much. It gives me great pleasure to introduce our speaker. This is Dr. Eric Perlman. He got his undergraduate degree from, and I'm blanking out, Occidental College.
You got it.
And then his Ph.D. degree from the University of Colorado at Boulder. He joined us in 2006, and I'm a big believer in short introductions, so let the speaker speak. So Eric, take it away.
All right. Thank you, Matt. And today I want to talk to you about something that is, for me, completely different. And I'll explain why in a few minutes. But it's about using astronomical observations to probe the structure of our universe. And what I don't mean is what you're used to hearing on this topic. You're used to hearing the use of astronomical observations to talk about cosmology, to talk about the large-scale structure, to talk about what the Hubble constant is, or how clusters of galaxies and galaxies form. That's not what I'm going to talk about. That's what I might more usually talk about because I work on distant galaxies and quasars and active galaxies. So getting involved in a topic like this, for me, is a big departure. And so not only am I going to tell you about the topic, but along the way I'm going to tell you how I got involved in it. Because this is a great story, I think, of serendipity and about how you can never leave your blinders on and ignore the bigger picture. So, there we go. The key questions that you want to think about when you're talking about the fundamental constants and the structure of the universe are these. First of all, what is the underlying structure of the universe on the smallest scale? And this structure can take a lot of different forms. Can it be, for example, foamy? Are there extra dimensions, some of which might be large, some of which might be small? Most of the superstring and supersymmetry theories that are out there, which attempt to unify the four forces of the universe, rely on extra dimensions which are too small to see. Dimensions which, we only perceive 4 dimensions, 3 of space and 1 of time. We can't normally perceive them, but they might be there. We, in order to actually translate these theories from things that might be interesting mathematically into real physics, we have to have ways to test them. Astronomical observations are one way that we can test them, and I'm going to explain to you how that can be done. Also, we want to think about whether the laws and the constants of nature actually are constant with time. Now that may seem a little bit abstruse, but it's very important for a number of reasons. First of all, what are these? Well, these are things like the speed of light, the gravitational constant, fine structure constant, things of that nature. And what they do is they control how strong forces are, they control the coupling between forces, the coupling between energy levels in atoms. If they were not the strength that they were, perhaps fusion wouldn't start in stars. Perhaps we wouldn't be here. Life would not exist in this universe if we had a different set of constants. So why am I interested in the subject? I told you I'd tell you about this because it's a big departure for me. I was interested, and unfortunately, this is not a great version of the picture. I was interested in the subject, I got interested in the subject very much by chance. I was working on a series of papers on distant quasars, and I was studying this particular object, Parks 1413 plus 135. This is an image from the Hubble Space Telescope with two different contrasts, basically. And this object here, also this one, that's Parks 1413. It's a very bright quasar. This is an infrared, near-infrared image at a wavelength of 1.6 microns. It's important to say that it's near-infrared here because this quasar is highly extincted. It's behind a lot of gas and dust. It is also in a spiral host galaxy. If you look closely at this image, you can see that the host galaxy is very elongated. In fact, it's an edge-on spiral galaxy with an enormous dust lane. And if you do measurements in the H1 line, which was one of the things that I did for this paper, along with the HST observations, you find that it happens to be behind a huge H1 region, which is also a giant molecular cloud complex the size of the Orion Nebula. So that is why I was interested in this object. And so I came along, I wrote a paper, and one of my collaborators on this paper used the H1 observations to do this. And yes, I'm on the list, but I really didn't do all that much to the paper. What he did is something that we're going to talk about later. If you have gas in front of an object, you can use the quasar as a backlight. And if you know the wavelength of your line very well, and we were using the 21 centimeter line of hydrogen here, and if you know the redshift of your object very well, then what you can do is you can go back and you can try to measure the evolution of the things that control that line, i.e., in this case, the fine structure constant. Okay? Now, a couple years later, Richard Liu and Lloyd Hillman at the University of Alabama in Huntsville came along and they wrote this paper. Well, I knew nothing about the subject. This piqued my interest even more. And what they did is they seized upon something which, when I was writing the paper on Parks 1413, I just said, oh, this is an Airy disk that I see in this image. Let me go back. Sorry. We'll go to that in a moment. I need to go back. I see an Airy disk here. Everybody see this? Okay. Do you know what Airy disks are? They're a fundamental thing that you get in a telescope, okay? It's a product of diffraction. If you're looking at an unresolved source, you should get an Airy disk. Okay, I commented that there is an Airy ring here, and I didn't think any more of it. Well, Liu and Hillman came along and they said, oh, if there are extra dimensions in the universe, then for a distant enough object, there shouldn't be an Airy ring, because the object should appear not unresolved, but instead it should have a halo. I'll explain why it should have a halo in a little bit. Turns out their argument was wrong in the details, but it was right in its motivation. Okay? So that's how I got involved in this game, and I got involved more seriously when one of their critics, one of Liu and Hillman's critics, wrote a paper, and I happened to be the referee of that paper, or one of the referees from the astronomy side. There were 3 referees to that paper. I commented only on astronomical things, but after the paper was accepted, I approached them with the idea to test it using observations of very distant quasars with the Hubble Space Telescope, which is one of the topics that I'm going to be talking about this evening. Okay? So, fundamental constants. Fundamental constants are important, as I said, because they control the strength of the forces in the universe, the coupling between the forces, and ultimately the things that we rely on for life. Fusion from the sun, okay? Various other things, the strength of the gravitational constant. All right, so it turns out that fundamental constants are actually difficult to measure. And the most difficult of them to measure is the gravitational constant. And the reason why it's so difficult to measure is because to do the measurement right, you actually need to in some way insulate or isolate your apparatus or separate out all of the other gravitational forces that are on it. Okay? You're going to measure out the gravitational constant. Well, you use it using a couple of masses that you know the mass of to exquisite precision, right? Well, problem is that you have the Earth. The Earth has an enormous gravitational pull compared to the two masses upon each other. So would the table that they rest on, or anything else in the room, and somehow you have to account for these things. And so it's actually a very difficult measurement to make. Now, the usual apparatus is a torsional balance, okay? And there are various ways that they have to deal with them, and that's a subject for somebody else's talk. I don't want to talk about that subject today. However, even when you have done those things, the fact is that you're making a measurement which is reliant on something else, and the reason you're making a measurement that's reliant on something else is because you rely on light to measure the distances that are involved and to measure the rotation of the balance. Well, you do this via interferometry. Guess what you need to know precisely, to very high precision, to do that? The speed of light. Okay, so in the process, you're introducing yet another dependence. And every measurement of every constant, unfortunately, is fraught with difficulties like this. The measurement of the gravitational constant is probably the worst of them. However, unfortunately, these measurements are fraught with difficulties. It's not easy to make a clean measurement of a fundamental constant for that reason. Okay? Hello? All right, so here's where astronomical observations come in. And what we're testing with astronomical observations are both the large and the small scales. Things like, for example, whether objects move in the same way in response to gravity on the largest of scales, which is the weak field limit, as they do on the small scales in the strong field limit. Now, this is the subject of another theory called MOND, which is not going to be something I talk about. I can comment on it if somebody asks about it, but it's not going to be my main topic today. You can also look at the lines. If there is an absorption line or an emission line in the spectrum of your object, you can ask whether its rest wavelength, i.e. in the frame of the object where it actually happened, is the same as the rest wavelength that we measure here on Earth. Sounds like a basic topic. Actually not so basic. Okay? It's a very important topic. Many of the lines are controlled by the coupling between quantum numbers. Okay? And if that's the case, you can use these to measure the fine structure constant. Now, the fine structure constant is actually a combination of fundamental constants, as I'll show you, but it's a very important number in its own right, and it gives you a nice window into the physics of the universe. Also, one of the things that you have when you have a very distant object is you have a long path length between you and that object. If there are extra dimensions, little cells in the universe, and in fact, I think, yeah, I've got an illustration. Here's a background quasar. And you can imagine that along your path, you have, number one, a large distance. Number two, that path, even though it sounds like it's empty, it's not really empty, okay? In fact, there are distant galaxies, and even more so than distant galaxies, there are also smaller clouds of gas, what we call Lyman alpha forest clouds, that are along the way from us to that galaxy. We can use both of those facts, okay? So if, for example, light is traveling from that quasar to us, and space-time actually has a foamy structure where there are small extra dimensions, okay? So let's say, for example, superstring theory is what actually is what governs the unification of gravity with the other three forces. Well, superstring theory requires 10 dimensions. The other 6 dimensions are very tiny, okay? And what's going to happen? At any point, there is going to be loops, okay? This is an illustration, a very blown up, exaggerated illustration of what this might look like. Okay, so put yourself along a path from this distant quasar and to us. Okay? You've got a very long path length. Along the way are many, many such loops. Okay? And so let's say you're here and the quasar is over here. And what does light do? Light spreads out from the quasar isotropically, right? Goes out in all directions. Now, normally, the way we look at space-time, we say, oh, light seeks the shortest distance between 2 points, because there is only one shortest distance between 2 points. Well, if space-time is foamy, that's not correct. There is more than one path between 2 points that light can take. Why? Because as you travel from here to here, there's lots of different points. There's lots of different paths. Light can travel straight, or light can travel along one of these loops, or within loops within loops. And that does a number of things to your observations, as we will discuss. That is what we would like to measure if you want to measure whether the universe actually has these extra dimensions. Well, how do astronomical observations help? You got more of these loops because you've got a much longer path length. And so, even though the effect of any one loop is tiny, you get a cosmologically large distance, billions of light years. Suddenly, maybe you've got a fighting chance to detect the overall effect of many, many, many of these loops because of their cumulative effect on the light from your distant object. So the first topic I want to talk about is the fine structure constant, because that's what got me into the game first. Okay? Now the fine structure constant is a coupling constant, and it is actually a combination. It's not one constant, right? It is this ratio here. Okay? And as you can see, it involves E, charge of the electron and the charge of the proton. It also involves the speed of light. It involves h bar, Planck's constant. So it's a combination of things. Okay? But what it does is that it's a coupling constant for the forces, for the energy levels within atoms, and it helps to measure how strongly light interacts with the particles that we have, say, in this room. Okay? So it's a very important constant. And it's known to exquisite precision from laboratory measurements. And so this is the value of 1 over alpha. And I'm quoting it this way simply because remembering this 137.035 blah, 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 blah is much easier than quoting it the other way, or at least a lot of people think of it that way. So does this remain constant over long periods of time? Here's where the advantage of astronomical observations come in. What we do here is we make use of the fact that the path between the quasar and us isn't empty. Okay? There can be absorption from within the quasar, as there was in the case of Parkes 1413. Okay? With Parkes 1413, we had H1 observations. As I said, the quasar lies behind an enormous molecular cloud region. We can make use of that. Okay, that's what my collaborator Chris Carilli did in his paper. You can also make use of all of these Lyman alpha forest clouds that are between us and the quasar. Not associated at all with the quasar. Some of them are associated with the outer regions of distant galaxies. Some of them are galaxies that basically are too small and they never formed. We can use those. That's what we're going to do. So Parkes 1413 plus 135. Let's take advantage of the weird properties. What you're seeing here are observations, results from the H1 observations with the VLBA. Okay? And you're looking at them two different ways. First of all, this is the integrated line. And by the way, you're looking at it in reverse. So you're actually looking at optical depth here, increasing along the x-axis. So if you're actually looking at it in intensity, it would be a dip. Okay? And you can see that the line is actually quite narrow. Here is the frequency as we measure it. Okay? And here are the contours in 4 different velocity slices. Each velocity slice happens to be about 4 kilometers per second wide. And the core of the quasar is actually this component right there. So you can see that the core, just by serendipity, lies right behind one of the thickest parts of this cloud. This cloud has also been seen in molecular lines, by the way. So my collaborator Chris Carilli did this, and basically he set a limit with this object and with another object of 3.5 times 10 to the minus 15 per year on the variations to a look-back time of about 4.8 billion years. Now, 4.8 billion years, it turns out that's the look-back time actually to the other object in this sample because he used 2 objects. This was the nearer of the 2. The other object was very similar in having a big H1 and molecular cloud right in front of the quasar. Actually, that was in an intervening galaxy in that case. But the same observation is possible in that case. And so that is what the 4.8 billion years refers to. And so one of the things that you can do with this is that we can think about what it is that produces the fundamental constants. What produces the fundamental constants in string theory, if string theory is actually the correct paradigm, is that it's actually the coupling between the dimensions, the scale factor of these compact dimensions. Now, this is not something I'm an expert on, okay? As I said, I work on quasars, and I really can't comment on superstring theory in its particulars. But the fact that you can use an observation of a very distant object to place a limit on the scale factor of very tiny additional dimensions that we can't normally perceive is fascinating. Absolutely fascinating. So, interestingly enough, this is not the only thing that one can say about this. We did this in the radio, okay? And we did this with lines from molecular clouds, in one case associated with the quasar, in one case not. And a different team in Australia, headed by John Webb and Mike Murphy and a bunch of other people, is using the Lyman alpha forest and other lines in the optical and ultraviolet to do the same kind of work. And they use the Keck telescope and the VLT to do this work. And so basically, every one of these clouds is associated with every one of these lines is associated with one of these clouds that is between us and the quasar. Okay? Now, most of these Lyman alpha clouds have only one line that we see. We only see the Lyman alpha line of hydrogen because they're not very large, okay? And they don't have many atoms, cosmologically speaking, compared to, say, a galaxy. The larger ones, we also see lines of helium or metals, carbon. Yes, to an astronomer, everything heavier than helium is called a metal. But we see these things. If we have multiple lines, that's when we can do the measurement, because then we can actually use the fact that we know multiple lines and their redshifts to actually narrow down the uncertainties that are involved. And so this is what Webb and Murphy and their collaborators have done in the optical with the Keck and the VLT. And they've done it completely independent from us. And so this is their plot of their constraints on delta A over A, or delta alpha over alpha, excuse me. And again, we're in units of 10 to the minus 5. And you can see, number one, they duplicate our result on the low redshift scale. Okay? We were talking about one object at 0.25 and another object where the absorption was at 0.7. So they're duplicating our result. But then there is a persistent signal that they are sensitive to at higher redshifts, longer path lengths, larger look-back times. Okay? And so while it is true that the measurement is a bit controversial, i.e. that there really is a deviation in alpha over long periods of time, the fact is that both could actually be correct, because on small scales they are duplicating our results. Now, as I said, in both cases it depends on knowing the redshift of the object to very high precision. It depends on having multiple lines. Also, though, interestingly enough, the Australian team, most of their objects are in one particular part of the sky. So it could be a peculiarity of that part of the distant universe. What that could be, I don't know. However, that is one possibility. Okay? And so, not sure the implication, well, we know that the evolution of the fine structure constant, if any, is tiny. It's less than 1 part in 10 to the 14 per year. If it evolves, it's evolving at 1 part in about 10 to the 15 per year. Okay? Now, in string theory, constants like these are set by the symmetry properties of the extra dimensions. So what we can do is we can work backwards, and we can use this to set limits on the scale factor of these extra dimensions. And basically, the limits that we can set, going back to the paper that Chris Carilli and my collaborators wrote, at that time it was 10 to the minus 15, and if you notice in the Webb and Murphy plot, their deviations are a factor of a few smaller than ours. So at the very least, it's less than a few times 10 to the minus 16, okay? In terms of this, and just after the Big Bang, this also goes down by a factor of a few. However, exactly what is varying, if something is varying, isn't clear. The reason why exactly what is varying isn't clear, go back to what the fine structure constant is. The fine structure constant isn't a single number, right? It involves the speed of light. It involves E. It involves h bar. So we don't know what's varying. E could be varying. C could be varying. And all of this depends on the assumption that the gravitational constant doesn't vary. And guess what? That's the least well measured of any of these. So that brings me to searches for a theory of everything and superstring theory. And this is a diagram of the forces of the universe that includes the energies at which they become unified and indistinguishable from one another. And as most of you know, there are 4 forces in the universe: gravity, the electroweak theory, the weak and strong nuclear forces, and electromagnetism. And some of these we are beginning to probe with particle colliders. The electroweak unification is being probed by Fermilab and CERN. But we can't probe any further up than that with particle accelerators that we currently have. Now, the standard model of particle physics successfully unifies these 3 forces: electromagnetism, the weak force, and the strong nuclear force. Okay? And it's made a variety of very nice predictions, and it's held up very well to scrutiny. But what it can't do yet is that it cannot unify gravity with those other 3 forces. And one of the reasons why is because gravity, as we currently know it, cannot be reconciled with quantum mechanics, number 1. And number 2, when you try to do this, you get all kinds of uncomfortable infinities in the calculations, and basically, it doesn't work. So nobody knows how to do this. And one of the ways that you can do this is by invoking extra dimensions. And this is what superstring theory does. Now, superstring theory, pardon me while I take a cough drop. Superstring theory is not the only idea out there, but it's one of the ideas out there. And superstring theory posits these additional dimensions, which are very small. And there is an old construct, even that came before superstring theory, called quantum foam. John Wheeler thought of the idea of quantum foam. If space-time is foamy, this is something that we can make use of the additional path length that would be provided by the loops that I was talking about to actually try to measure. So let's see how we do that. Okay? And just to give you another view of this, what we're after, eventually, or what particle physicists are after, is a theory of quantum gravity, a theory that explains all four forces in the same breath. We can't do that yet. And if we look at the structure of our universe on small scales and we imagine our three-dimensional universe as this ball, this two-dimensional construct that is this ball, and we say, okay, there are these extra cells, we can imagine this as all of these cells. And you can see that within, if you have one object here and another object here, and you're actually asking what paths light can travel to get from one object to another, there are multiple paths that can be traveled, some of which go through the foam cells, some of which don't. Actually, if you average over long enough distance, every path will go through foamy cells. And the many paths to an object through many different foamy cells. Just as in the illustration that we were looking at some time ago. So again, making use of this lower panel of the illustration, going from here to here, many, many different paths are possible for a given ray of light. And so even though it is traveling along what we call a geodesic, which is the shortest distance between any two points, there's multiple ways to do it. And so we need a way to, first of all, describe these foam models, and I apologize for getting a little technical, but unfortunately, in the next few slides, it is going to be necessary to do this. There is one main characteristic of them, and that is that they have a spectrum of fluctuations. And this parameter, yes, another alpha, controls that. And there are three main models. One is what's called the random walk model, and it's characterized by alpha of 0.5. And in the random walk model, the effects of space-time foam grow like a one-dimensional random walk. So if you imagine, the nicest way to imagine this is that you are a drunk person, and you're going out of a bar at 3 o'clock in the morning, and you've had much too much to drink. You don't proceed to your destination, wherever you're going home to, along a straight path. No, you're going to go back and forth and back and forth and back and forth because you're incoherent. This is basically what you're doing on a random walk, is that, okay, you take one step in one particular direction. Then you have an equal chance of going left or right. So you make another step. You have another equal chance of going left or right, and so on and so forth. Eventually, if you have a large number of particles, they diffuse out in a well-known way. And so this is what the random walk model does. Okay? There is another model called the holographic model. This is a model that is very much in vogue in some of these. What it basically contends is that if you've got a multidimensional region of space, you can encode the information content in that in a smaller surface. So for example, if you have a 3D region of space, you can encode the information content of that 3D region of space on a 2D region of space. Okay? And so this is consistent with what's called the holographic principle. This has a different spectrum of 2/3. And then there's a third model, which nobody likes because it's basically untestable, which is that these fluctuations are uncorrelated. They have no cumulative effect on the path length. That is alpha of 1. The length scale is just the Planck length, which is incredibly small. And guess what? We can't test that. In fact, nobody can test that as far as I'm aware. All right. Here's where I have to get a little bit technical because there are various ways of measuring distance. And one of the things that they depend on is not only this alpha, but also, you're measuring fluctuations in L. Each of the cells is the size of the Planck scale. And so if you do a Gedanken experiment, a thought experiment, and you combine quantum mechanics with general relativity, and I'm not going to go through the calculation in detail, you say, okay, well, space-time undergoes quantum fluctuations. This is what Wheeler did, by the way. Okay? And over a long path length, you should be able to measure them. Okay? You can do it a different way, invoking the holographic principle, and if you do it that way, then you're taking advantage of the fact that you want to measure the number of degrees of freedom in a given cell, which are the number of small cubes of, say, a given length in your small cell. That actually gives you a slightly different prediction. The two ways of thinking about it give a different prediction. This is related to these different models that we talked about. Now, it turns out that detecting what's going on isn't actually simple. The most simple way of talking about it was what Liu and Hillman did. Okay? What they did was they said, okay, we will use basically the holographic principle, and we will assume geometric optics and basically make use of every telescope as a single monolithic thing. By the way, they didn't take into account that you need to include the ability of your telescope to coherently sense a wavefront. Okay? So they thought you could do it with an image. You can't quite do it with an image because you need to be able to coherently sense the phase of your wavefront. You can do this if your telescope is diffraction limited, which Hubble is. So it turns out Hubble can test this, but not quite in the way that they thought that it could. Okay? So, what happens? Let's say you are traveling along one of these foamy paths with many possible paths between point A and point B. Okay, along each of these paths, there is a slightly different travel time for every photon. So what happens? That will mean that the photons arrive over a range of time. If there was a single event which triggered their release, they will not arrive as a single event. They will arrive spread out in time. Or, if the object is unresolved, what's going to happen if you ray trace it? It's not going to be unresolved. The photons are going to spread out, then they're going to come back, but not quite in focus. It's going to appear fuzzy. So either of those two things are things that you can look for. Now, either one is measurable. Of course, longer path lengths are better. What this diagram does, which is part of the paper that I wrote along with the collaborators that I gained basically from refereeing that paper, Jacking and Wayne Christensen at University of North Carolina. These are the halo size in arc seconds that you would get depending on wavelength of light. And so what is in here, each of these tracks represents the imaging capability, assuming that it is diffraction limited for a given telescope. Okay? And this track represents the random walk model. And basically, you can see that the random walk model is completely ruled out by all the observations that we've got. The fact that we observe unresolved objects at cosmological distances completely rules out the random walk model. Okay, and by the way, you see two sets of tracks for every alpha. Those two sets of tracks represent, for the one on the right, a redshift of 1. For the one on the left, a redshift of 4. Okay? So the random walk model, alpha of 0.5, is ruled out. Here's where it's getting interesting, though. We would like to test alpha of 2/3, which is the holographic model. Here's the Hubble Space Telescope. This was the germ of my idea. I said, okay, let's use the most distant objects possible to test it. Why? Because Parkes 1413 plus 135, Lewin Hillman's paper, that was here. Okay? And the reason why it doesn't get you as far as this is simply because it's only at redshift 0.25. If we can go out to redshift 4 or 6, we can go further. Well, that also revolves around going as far to the blue, into the ultraviolet actually, as possible. Now, interferometers, and in particular something like the VLTI, the Very Large Telescope Interferometer, can do better. That's what this is. VLTI actually just started seeing fringes between its 4 telescopes last month. So this is very much something we want to do in the next few years. The Chandra X-ray Observatory is dotted. This is actually quite important. You might think, and in fact, if you took Lewin Hillman's paper literally, you would say, oh, Chandra can blow all of this away. No, it can't. And the reason why it can't is because Chandra, despite the fact that it has half arc second resolution, is not diffraction limited. It does not sense the light coherently. And it's because of the very short wavelength of X-ray light and the way that it needs to be constructed as a telescope. That is why Chandra is a dotted line here. You might think you can use it, but it turns out you can't. Now, along the way, I should mention that there has been a recent claim by the people with the GLAST satellite, the Fermi Gamma Ray Telescope is the other name for GLAST, that you can use the time delays to do a similar measurement. Okay? The idea is what we just talked about, that if you have multiple paths, you're going to have different arrival times for different photons that were triggered by the same event. And what they did was they used a very bright gamma ray burst to do their test. However, we beg to disagree with them, and the problem is this. If you go into the details of the calculations, the way foaminess shows up is it shows up to us as a variable speed of light with equal plus and minus departures as you have basically random departures either way in your foamy cells as the light spreads out. You can calculate the amount using the Heisenberg uncertainty principle, and it turns out to be way too small to be detectable with the time resolution of Fermi. So for the alpha of 2/3 holographic model, it turns out that we would predict a dispersion of 10 to the minus 23 seconds. Forget it. So that's where these folks were wrong, okay? And that's also where our paper comes in. Okay, so the utility of higher redshift observations is the long path length, but you can only do it if you can use your telescope to detect light coherently. And because it basically makes the object appear like it has a halo, it's actually a difficult observation to do, okay? Because lots of things can appear like a halo. In particular, with a quasar, quasars are in distant galaxies. That galaxy can appear like a halo. We need to separate that out. What we make use of is a quantity that we know from optics called the Strel ratio. That measures the ratio of the peak of the observed flux to what it should be theoretically. And qualitatively, this is the sharpness of the peak. And what it allows you to do is to test this theory without having to look for anything like Airy rings, as we did with Parkes 1413 plus 135, and without being fooled by the host galaxy. And so this is what the Strel ratio as a function of redshift and observing wavelength would look like. And you can see, this is for the Hubble Space Telescope, by the way, you can see that really, as you go into the ultraviolet, it gets much, much better. So here's where our paper came in, and this is just published this last month in Physical Review D. And what we did was we went into the Hubble Archive and we used observations of very distant quasars. These are quasars at redshifts of 4 to 6. They're the most distant quasars that the Hubble has observed. And these are images of them in 4 different bands. And we also have, if you go, anyway, we also have here the point spread function that we want to compare to. So this is what we're taking the ratio of and computing the Strel ratio. Okay? And this is what you get when you deconvolve it. And this next plot and we want to focus in on this track, basically tells us that our constraints basically get us to alpha of 0.655. Not quite to 2/3, but almost. So the holographic model barely still is okay. If we could go to the ultraviolet, we could rule it out. The problem is this. In the ultraviolet, observing a distant quasar is actually very difficult. And the reason it's difficult, if I can go back a number of slides, is the following. I should have put that right next. I should have put that slide right after, but I didn't think to do that. If you're observing in the ultraviolet, you're observing through this. You're trying to look at the integrated flux of your quasar when it's all been eaten away by these Lyman alpha forest lines. That's the problem. So the object is much fainter because of that. And so for that reason, the observations become enormously more difficult as you go to the ultraviolet for the most distant of quasars. Whoops. Anyway, sorry about that. All right, it's not going to let me. It's not going to let me. PowerPoint is a funny thing sometimes. PowerPoint is a funny thing sometimes. Is that going to let me do that? Yes. All right, so basically, even though we need shorter wavelength observations, unfortunately right now we're nearly at the end of what Hubble can do for this. If we have the VLT, we're actually going to be writing a proposal hopefully for the VLT to do this with its interferometer, and that can hopefully help us to test this further. Could the two measurements be measuring the same thing? Well, yes, perhaps, because the fine structure constant variations could actually be a variation in either c, the speed of light, or e. We can rule out c because it would be too small to be detectable. And if you think about it, the Murphy and Webb results require changes of 1 part in 10 to the 6th over this time period, and that's much too large for what we see. But if it's E, or if it's something else, then A, they could be measuring different things. B, we don't know. So we don't have a firm answer. What we do know is that despite the fact that we are measuring two very different length scales by going to the very most distant objects, the fact is that astronomical observations hold considerable promise in a fascinating way for giving us clues to the fine scale structure, the smallest scale structure of the universe and its laws. And so with that, I will go ahead and go to my final slide, which basically just tells you why we need to think about it beyond the overall fascination of it and the laws of the universe. I mean, for somebody like me, or for a particle physicist, that's plenty. But many people like to think about what might happen for life, okay? If the laws of the universe were different. Well, maybe fusion might not have happened. If the constants were different, if the gravitational constant was different, maybe fusion would never have happened because stars could not be dense enough for fusion to happen. Or if it was too strong, then what would happen? They would fuse hydrogen at too fast a rate, and there would not be a long enough time period for life to develop here on Earth. This is what some people have described as the anthropic principle. I don't know if I put any more stock into it than that. Some people have written very long philosophical treatises on it. We can't say anything about this directly. However, it's a fascinating thing to have philosophical discussions about it. And with that, I will take your questions.
All right, thank you very much, Eric.